Certain substances will react with acids to produce gases, and many of these reactions are fun to play around with in the chemistry lab or even at home. One that you can play with at home is the bicarbonate of soda Volcano, otherwise known as the bicarb Volcano, which involves mixing household vinegar with some baking soda or bicarbonate of soda to produce carbon dioxide gas, along with a couple of other products. And if we mix in a bit of food colouring and add a bit of liquid detergent, both of which take no part in the reaction, we can actually get some quite neat visual effects from this reaction, with the carbon dioxide gas bubbling up through the liquid detergent to produce a volcano foam, as we can see here. The active ingredient of vinegar in this reaction is the weak acid ethanoic acid, more commonly known as acetic acid. The active ingredient of baking soda is the ionic compound sodium hydrogen carbonate, and the products of this chemical reaction are the salt, sodium acetate, the gas, carbon dioxide, and liquid water. If we look at these substances in a bit more detail, we can see that the acetic acid dissolved in water produces the hydrogen ion, characteristic of all acids, and the corresponding counter-anion in this case is the acetate ion, C2H3O2-. If we look at the structure of the sodium hydrogen carbonate ionic compound, we can see that it is comprised of the positively charged sodium ion and the negatively charged hydrogen carbonate polyatomic ion. This gas-producing reaction is actually a further example of a double displacement metathesis reaction, with the acetate ion displacing the hydrogen carbonate ion to form the sodium acetate salt, while at the same time the hydrogen ions from the acid are displacing the sodium ions in the sodium hydrogen carbonate, coming together on the right-hand side of this equation to form carbon dioxide gas and liquid water. So what we have is an acid plus a hydrogen carbonate salt producing another salt plus carbon dioxide plus water, one of the more famous and favourite reactions involving gas formation. And remember, a hydrogen carbonate salt is any salt containing the hydrogen carbonate ion. It turns out that hydrogen carbonate salts are not the only salts that produce gas in the presence of acid. For example, any carbonate salt will react with an acid to produce a different salt plus carbon dioxide gas and water. And remember, a carbonate salt is a salt, or an ionic compound, that contains the carbonate ion, CO3 2-. Sulfite salts will also produce a gas in the presence of an acid. An acid plus a sulfite salt will produce a different salt plus sulfur dioxide gas and water. And remember, we identify a sulfite salt as an ionic compound containing the sulfite ion, SO3 2-. Sulfide salts will also produce a gas, hydrogen sulfide or H2S, in the presence of an acid, with the general reaction scheme being any acid plus a sulfide salt produces a different salt plus H2S gas. And we should also remind ourselves that we identify sulfide salts as ionic compounds containing the sulfide S2- ion. And just be aware if you try this reaction, since H2S gas is also known as rotten egg gas, and the reaction is best carried out in a fume cupboard. Lastly, and perhaps the most important type of acid reaction involving gas formation, is the reaction between an acid and a reactive metal to produce a salt and hydrogen gas, or elemental hydrogen. And at this stage of our chemistry understanding, we will define a reactive metal as any metal that reacts with an acid to produce hydrogen gas. Now, I know that sounds like a bit of a self-fulfilling definition at this stage, but we need to understand a bit more about electrochemistry and redox reactions before we can refine our definition of a reactive metal. So here we have a summary of 5 generalized reaction schemes for substances that react with acid to produce some type of gas. In each case, we typically need to be able to predict the products that will form when one of these classes of substances reacts with an acid. So, for example, if we come across any of these general reaction types, we will learn through practice to recognize them and understand that they are gas-producing reactions. And we will be able to immediately write down these products over here on the right, the gases that are produced as well as any associated waters. For example, if we add an acid to a carbonate salt, we will know that both carbon dioxide gas and liquid water is produced, and we can write them down straight away. Likewise, if we add an acid to a reactive metal, then we will know that hydrogen gas is one of the products, and so we can write it down straight away. The trick then is to work out the identity and the formula of the salt that will be produced for each specific reaction. And if we recall that a salt is an ionic compound composed of cations and anions, we will come to understand that the cation will be derived from these substances here, while the anion will be derived from the specific acid employed in each reaction. And this is best demonstrated by example. Let's start with a general reaction scheme of an acid plus a carbonate salt producing another salt plus carbon dioxide plus water. If we choose a specific acid, say nitric acid, and we choose a specific carbonate salt, say sodium carbonate, we know that any acid plus any carbonate produces carbon dioxide and water, and we can write these products down straight away. The trick now is identifying the salt that is produced. We saw earlier that these reactions are displacement reactions, with, in this case, the nitrate anion from nitric acid displacing the carbonate anion from sodium carbonate, producing the salt sodium nitrate, NaNO3. So in effect, the metal sodium cation from sodium carbonate pairs with the nitrate anion of the nitric acid to produce sodium nitrate, which we have written here correctly, and we've also added the correct aqueous subscript in accordance with our knowledge and understanding of our solubility rules, which show sodium nitrate is a soluble salt. By now we should be able to see that this equation is unbalanced, with 2 sodium atoms on the left-hand side and only 1 on the right-hand side. We also have only 1 hydrogen on the left-hand side, but 2 on the right-hand side. And we balance this equation by placing stoichiometric coefficients of 2 in front of the nitric acid and sodium nitrate to give 2 lots of nitric acid plus 1 lot of sodium carbonate produces 2 lots of sodium nitrate plus carbon dioxide gas and liquid water. And if we need to write out the net ionic equation for this reaction, we can write down the full ionic equation, identify any spectator ions, and cancel them out, remembering that spectator ions are ions that undergo no physical or chemical transformation from one side of the reaction to the other. And what we are left with is our net ionic equation at the bottom. 2 H+ ions plus a carbonate ion produces carbon dioxide and water as the overall net chemical change that occurs. Let's have a look at another of the reaction schemes shown earlier, an acid plus a reactive metal producing a salt plus hydrogen gas. For example, if we choose hydrochloric acid, HCl, as the acid and zinc as the reactive metal, we know straight away that hydrogen gas will be one of the products, and the trick now is to work out what the identity of the salt will be. We know that salts generally contain a metal cation and a non-metallic anion. In this case, the metal will be zinc and the non-metal will be the chloride ion from the acid, resulting in the compound zinc chloride. Now, all chloride salts are soluble and will have the aqueous subscript, with the only exceptions being silver, lead and mercury, and zinc is not one of those exceptions. You will notice we have written down the chemical formula for zinc chloride as ZnCl2. This is because zinc, in its ionic form, will always be Zn2+. It is a type 1 metallic ion and therefore has only one charge associated with it, and it is always 2+ in its ionic form. And the chloride ion, as we know by now, is always 1- in its ionic form. When we do our crisscross method, we take the 2 from the 2+ charge of the zinc and bring it down as a subscript for chlorine. And we take the 1 from the 1- charge of chlorine and bring it down to be the subscript for zinc. So we get Zn1Cl2, or just ZnCl2 as the formula for zinc chloride. This equation is unbalanced. We have 1 chloride on the left-hand side and 2 chlorides on the right-hand side. And we have only 1 hydrogen on the left-hand side, but 2 on the right-hand side. To balance this, we place a stoichiometric coefficient of 2 in front of the hydrochloric acid, and we now have our balanced chemical equation written in the form of a full molecular equation. We can also write out the full ionic equation by separating out the individual ions for all strong electrolytes present. We can identify and cancel out spectator ions to get to the net ionic equation of 2 H+ ions plus zinc metal produces the Zn2+ ion and elemental hydrogen gas. Now, an interesting feature of this net ionic equation is that zinc metal starts with a net electronic charge of 0, as would be expected for an element, but ends the reaction with a net charge of +2. Also, hydrogen starts the reaction as the +1 hydrogen ion and ends as the 0 charge elemental hydrogen gas. Reactions in which the electronic charge of substances change during the course of a reaction are a subset of a special type of reaction called redox reactions, which will be the subject of the following video in this series.